I'd like to thank the organizer for inviting me to present in this great symposium. I'm Jianwei Huang. I'm a postdoc in MINIS group. So the title of my talk today is this orbital-selective correlations in this iron tellurium selenium series. I will call it FeTeSe for short. So first of all, I'd like to acknowledge our collaborators, which our APEX experiments was assisted by Donghui and Makoto, Jonathan and Sangkun. Our theoretical calculation was done by Rong, Ximiao, and Jianxin. The whole resistivity measurement was done by Junhao's group, and our beautiful samples was provided by Zijun, Genda, and Peng Chen's group. So first, I will quickly recall the basic property of the iron-based superconductors. So here I'm showing these body standard tetrahedral crystal structure of this archetype iron-based superconductors, berry iron arsenide. It is generally agreed that the iron nictrogen layers is critical as it is the building blocks of all the iron-based superconductors, and is where the low energy electronic structures originate from. DFT calculations have shown that the iron 3D orbitals occupy the lower binding energy, which is around Fermi level, while these nitrogen p orbitals occupy the higher binding energy. Furthermore, the nitrogen crystals split these 3D orbitals, which make the three T2G orbitals lifted slightly above these EG orbitals. Eventually, what we will see is the Fermi, the electronic structures around Fermi level is mainly consist of XZ, YZ, and XY orbitals, which will form this whole pocket around the gamma and the electron pockets around the beryllium zone corner. So it is generally believed that the iron-based superconductors possess this moderate electronic correlation strength. It is not as strong as that in the cuprates, but it is definitely non-negligible as in this simple matter state. So the moderate electron correlations of the iron-based superconductors are manifested by its bad matter behaviors. For example, they have a larger resistivity compared with the simple matter, and we observe these suppressed peaks in the optical conductivity spectrum, and we see this large ordered moment or the large fluctuation moment in the iron-based superconductors. There are two things that we know about these correlations for the iron-based superconductors. First is the iron chalcogenide basically possesses larger electron correlation effects than the iron pnictides. Second is the electron correlations in the iron-based superconductors exhibit this orbital selective behavior, which the XY orbital, the band of the XY orbital always exhibit a larger mass enhancement than other orbitals. Later, it was found that actually the electron correlations in the iron-based superconductors can be related to these iron nitrogen bound lengths. It can be understood that in a way that the iron hoppings through these nitrogen atoms was reduced by increasing this iron nitrogen bound length. So especially in this iron chalcogenide, which possess larger electron iron nitrogen bound lengths, we find that in this iron tellurium selenium compound, the DXY orbitals experience a very larger mass enhancement. With which we can find that its quasi-particle coherence factor reduce close to zero, while the orbitals still possess considerable spectral weight. It is these strongly orbital selective correlations really sits very close to this orbital selective model phase, which the DXY orbital totally gone. So actually, the orbital selective model phase was theoretically proposed to exist in these iron-based superconductors. Orbital selective phase generally was describes like in a multi-orbital system, particular orbitals turns are localized while the others still remain itinerant. In the case of iron-based superconductors, it is the DXY orbiter localized, but all the other orbitals remain itinerant. Three conditions are need to realize this OSMP state, which first we need the crystal field to split the XY from the XZ or YZ orbitals. Then the XY bandwidth need to be smaller than XZ and YZ without considering the electron-electron interaction. Third, we need a Huang's coupling to suppress the interorbital interactions so that the different orbitals cannot talk to each other. With all this, we should ask these questions. Can we really realize an orbital selective ground state in the iron-based superconductors? So in the following talk, I will persuade you that we really find that this iron tellurium is in proximity to the orbital selective mode ground state by first present you this universal OSMP crossover induced by temperature. Then we show that there are four observations that really tell us the FT is in proximity to the OSMP ground state. First is this selective divergence of this band effective mass. Then we find this redistribution of the Fermi surface spectral weight. The third thing is that we find that the DXY incoherence temperature decrease toward this iron tellurium end. The third is to find our RPS observations consistent with this whole resistivity measurement. First of all, this temperature-induced orbital selective mode phase has already been found previously. This is a gamma M cut. Sorry, this is a gamma M cut for this FTS with selenium content equals to 0.44. We find that the low energy band consists of these XZ, YZ, and XY orbitals at the low temperature. With the increase in temperature about 120 Kelvin, we find the spectral weight of the DXY orbiter near Fermi level is strongly suppressed. And concomitantly, we find that the gap at the endpoint, which is caused by the strong hybridization of these XY orbitals with the XZ orbitals, also disappear. To quantitatively analysis this, we plot the spectral weight of the XZ and YZ orbitals by fitting the EDCs across these at this yellow bar position, and we find indeed the XY spectrum weight decreased to 0 at around 110 Kelvin, but while the YZ orbital still remains considerable spectral weight. Later on, our experiment also will captured by the theoretical calculations. And later on, the temperature-induced orbital selective mode crossover was found to be universal in these iron chalcogenide families. No matter, despite they have different crystal structures and different Fermi surface topologies, you always find the DXY spectral weight drops to 0 with increased temperature, with YZ still possess considerable spectral weight. And besides RPS, there are also other props that report this orbital selective mode crossover induced by temperature, like this combination of the resistivity, heat capacity, thermal expansion, and susceptibility. Also, this orbital spectroscopy measurement on this potassium iron silicon. So now I'm going to show you how we've tuned this tune towards OSMP ground state by reducing this selenium. First, we have shown that we have previously shown that in this iron tellurium selenium, the optimal compound, we can induce this OSMP state by increasing temperature. Then how do we, what if we tune across this x-axis? In this previous diagram, we find that we substitute a selenium with tellurium, the ion bond will increase. So the XY orbital seems to go will undergo a much larger mass enhancement. So we plot we did this experiment. We plot the gamma M cut of different iron tellurium compound, which shown this shown in this phase diagram here. To better all these cuts was taken at low temperature around 10 Kelvin. To better show the band dispersion, we take a second derivative, and we fit this band with a parabolic curve to extract the effective mass. First, let's take a look at the DYD orbitals. We find that the effective mass of the DYD orbitals does not change much. But for the XY orbitals, we find a much stronger effective mass towards iron tellurium end. We plot our fitting results here, and indeed we find a divergent behavior of the effective mass enhancement towards this iron tellurium end. And then we plot this quasi-particle cohesion factor extracts from this effective mass enhancement. We find that it decreases, and a linear extrapolation tells us this Z extrapolates to around 0 at this iron tellurium end. Second, we observe this strong Fermi surface spectral weight distribution. So the right figure shows the optimal doped compound, which shows the hole pocket around the gamma and electron pocket around M. This is normal. But for the iron tellurium, we find that there is spectral weight appears around this X point of the Brillouin zone. So where does the spectral weight of the X point evolves? We plot this systematic evolution of the Fermi surface. First thing we see is these the electron pockets expand from the iron selenium to iron tellurium. Then we find that the phaeant dxy orbital, the spectral weight gradually evolves to this spectral weight around this X point. To quantitatively extract this spectral weight evolution, we integrate this spectral weight around this inside this rectangular, and we plot the spectral weight evolution here. The evolution really reminiscent of the effective mass evolution we have shown before. So this really shows us that this iron tellurium is really in proximity of this OSMP state. So then here is the question. So where is this spectral weight come from? So our theory collaborators have done these calculations based on this U1 slave spin theory on this multi-orbital Hubble model. So for this x equals to 0.5 FTS, this state is in this this sample is in this strong correlated matter state. Well, we find that this square orbital which cross this Fermi level around this X point is gapped by the hybridization with XY orbital. So in this case, it shows this normal Fermi surface with the hole pocket around gamma and electron pocket around m. But when the sample went into this OSMP state, the dxy orbital becomes totally localized. Then the square orbital cross the Fermi level, and the spectral weight around X point appears. Their calculation shows a great consistent with our experimental observations, and with all this, let's take back to look what we have learned. First, this is the phase diagram with this TC, TS, TN. At the ion selenium end, we find that it is a strong correlated matter. With increasing temperature, the dxy orbital will become incoherent. For this iron tellurium compound, it is in proximity to this OSMP state. It's a ground state. So suppose we go from the iron selenium to iron tellurium, we will expect a decrease of the dxy orbital coherence temperature. So let's check whether this is the case. We plot what we have do before. We plot the spectral weight of different orbitals from two different samples of the FTS, one with a higher selenium content, one with a lower. We find that the FTS with a higher selenium content shows a higher dxy incoherence temperature, but for the compound with a lower selenium content shows a lower dxy incoherence temperature. So this really agrees with the iron tellurium as a OSMP ground state well. And with this, we come to our brief conclusion with a summary, which first we observe this dxy orbital become totally incoherent with increasing temperature. Second, we observe this the effective mass enhancement, that it diverges towards this iron tellurium end. Then we find that these are a redistribution of the Fermi surface spectral weight, which is very likely induced by this incoherence of this dxy orbital. Third, we find that the dxy incoherence temperature decreased towards this iron tellurium end. So we draw this conclusion that our iron tellurium is in proximity to the OSMP ground state. And this is not the end. We have done this Hall resistivity measurement on this FTS series. And we find that this common feature is that the Hall resistivity as a function of temperature shows a hump and a side change. So there are two interpretations of this behavior. One is this hump and the side change is caused by the incoherence of these dxy portions of the electron pockets around the endpoint. The second interpretation is that it's the suppression of these pi fluctuations with this dxy incoherence. Both interpretations also tells us that these characteristics temperature really marks where the dxy orbital become incoherence. We plot this correct temperature here. It's really the trend really matches our RPS evolutions well. And so based on all the observations, we draw the conclusions that these iron tellurium and compound is indeed in proximity to this OSMP ground state. So that's all. Thank you. I didn't put the band structure evolutions here, but I have it in the supplement if you want to look. Oh.
Okay. Yeah. Thank you.
I have the same question I asked before. What's the value of the crystal field splitting? That's a number, you know the number. And why do the people who do iron selenide claim that the XY orbital is below the XZYZ?
I think we agree with that, Gabby. So our iron selenide side, is indeed below the XYZ. I don't think there's inconsistency on that side.
Well, but in all the calculations that they show me with this model, that's not happening.
So, oh, right, yeah, here is the hybridization slide, right? So I guess the rightmost doping substitution level, you can see the hybridization between the XY whole band and the XZ.
So let's see, do you have a pure iron selenide in this? No.
I guess we don't, yeah.
Because it would be really wonderful if the experimental groups can agree on the facts. I tried to lay out the questions for the theories, and you should measure the volume of your Fermi surface. It's really easy. I convinced Humiao to do the integrals. You have a great student, he can do the integrals, and then you get a number.
But Gabby, I mean, they have done a polarization study for you, and they have identified at low energies near the Fermi energy where the XY states are and where the XZYZ states
Yeah, I just
are.
want a
So you
drawing
can,
of the Fermi surface. The polarization has nothing to do with it. The polarization just tells you what.
no, there is a Fermi surface, right? The Fermi surface will show the contrast between 50-50 and FeTen is something that you see by the naked eyes. And there's a big pocket near X that's developing near FeTe that's not there in 50-50, right?
Beautiful. So I like that because that's the
yeah,
that's the cleanest example that there is an orbital selective mod transition. There is a violation.
And I thought Gabby, you would like it in the following sense. You know,
no. That is getting contradictory information from different experimental groups. That's why.
Well, the other experimenters are not speaking here, so maybe we should bring in the discussion in a different forum. But what I want to draw your attention to is that there's some beautiful evolution of the Fermi surface that in other materials, such as heavy fermions, it's very hard to use APAS to see, right? Here, you are visualizing the K-space directly, and there's something to be understood. Why there's a big region near X that's developing as you go from 50-50 to FeTe. And I was very surprised for a long time.
My request is to add to this the iron selenide, so we have a complete.
No, it would be nice, but already you have this contrast. They worked very hard for this.
And then I would like to have the not just the drawings, but then the integral, which is just a number, just to see what it's just a test on the experiment, just to see by how much it jumps. I just cannot do the integrals in my head. That's just some suggestions how to analyze the data.
I think a Luttinger volume would be extremely beautiful to analyze, but you know, having thought a lot about Luttinger volume in the context of heavy fermions. Here, the background conduction electron states, they are a curse and they are an advantage. The curse is that you have dxz, dyz, dz square, and you have 4 d band orbitals, which are all from the perspective of orbital selective mod, acting as a background conduction electron states. The advantage is that something like a z square you can really track. So there's some well-defined the analog of what we call the SPD states of the heavy fermions that you can zoom in and these they spend a lot of time looking at it, and turns out that's extremely illuminating. In other words, you can look for hybridization and its breakdown near gamma, and experimentally it's very hard, and there's some feature that's there. It turns out the breakdown hybridization is just in your eyes if you look at the right place, which is look at near X, where the dz square crashes down or not, depending on whether the hybridization is there or not. So there's something experimentally extremely beautiful there from the perspective of Luttinger volume without looking at the much harder issue of counting Luttinger volume, which is very nice to do, but much harder.
Yeah,
Okay.
I'm just making some obvious suggestions that it's really important. In gamma, we understand everything, so we should know the order of the levels. I would like to know how large is the crystal field. I mean, just some basic things that can easily be done.
Any other questions?
Gabby, I think there is a practical concern from photoemission experiment point of view that it's far from obvious you can get an accurate Luttinger volume counting. On the one hand, there are so many bands in pnictides, it's very hard to precisely determine KF. And on the other hand, there is a three-dimensional Fermi surface, so you cannot just count the area on the map. You actually have to.
I know on lithium iron arsenide we did that job, you know. I mean, so I don't see any reason why it cannot be done. Here
it can be done. It's just the error bar has to be convincing.
Sure, and yes, that's true.
Yeah, I guess in this case the pockets are smaller than the lithium iron arsenide. The XY pocket is quite large. I guess I mean you're not gonna you're not gonna take all this things that were, you know, the experimental details that may add up, but we'll try. Yeah.
And I would like
Thank
to
you for the
also
suggestion,
your
yeah.
data on the iron selenide side. Then we have a comprehensive picture. I think it would be nice if the community can converge on what's known. I think this is beautiful work. I think it's really important. It's very nice. Just it becomes even nicer when when you reach consensus with the other groups.
Mm-hmm.
And I think it's,
you know,
sorry,
I was going to just add on point, if I may, just on this point. FeSe has a life of its own, Gabby, with pneumaticity and all that.
You measure at 100 Kelvin. There's no pneumaticity at 100 Kelvin.
We have that data. I mean, I don't think in terms of data we have any disagreement on iron selenium. We have done that work last year regarding to look through the Fermi surface through the phase transitions.
Yeah,
And
so
that,
like
yeah,
at 100 Kelvin, how does the XY orbital? Because you see the theories feed on that. There's a paper 1 week ago of Luca de Medici, which in fact I agree with, which is very nice, but it's all based on the fact that the crystal field levels got inverted in the iron selenide. And I would like to know if it's true. Mm-hmm. I mean, what I try to say in my talk is that if you look at it from the perspective of resources and the time that the community is spending on this and some rational way, there are some obvious questions that could be clarified.
I see.
think we should list that question.
Iron. Okay, yeah, okay.
I think we should list the crystal level scheme as part of the discussion questions. It's interesting and important. And how to make progress.
Whether to know the Luttinger liquid. I mean, yeah, well, that's actually an interesting point. Yeah. Any other questions? Okay, so if not, I mean, it's getting quite late. Yeah, let's thank all the speakers, and then
okay,
we'll
very
see.
Nice. Good to see you guys.
See you, Gabby. Yeah. So
thanks for staying all the way.
Yeah, continue this tomorrow. Yeah, thank you.